So Chapter 1, Basics of Measurements. In this class, we're going to be dealing with some very large numbers and some very small numbers. So science frequently pushes the boundaries of what our brains can imagine in terms of small and large numbers. So for example, all of the zeros in this big number of light years are pretty cumbersome. It's hard to tell right away what we should call that number, at least for me. I would have to count out, we've got thousands, millions, billions, 14 billion light years. That's a lot of light years. That takes a long time to travel. Scientific notation can compress this so that it's fewer things to write, and it's also a little bit easier to get the idea of how big is the number or to put it into our calculator. When we write a number into scientific notation, there are two parts. The first part is the decimal part. The decimal part comes first. The decimal part is a number that is between 1 and 9. Or sorry, 1 and 10. It does not include 10. It goes up to 9 and however many repeating 9s you can have after that, but it's never going to turn into 10. The idea with our decimal part is we've got one number and only one number in front of our decimal, and it's a non-zero number. So that's why it's between 1 and 10. And then you can have however many other things you want after that, however many you need. And then we also have the exponential part. The exponential part is the times 10 and then raised to some power. It can be a negative, meaning it's a small number. It can be a positive, meaning it's a big number. So small number, if it's a negative exponent, like the 10 to the minus 9 that we have there. Positive means that it's a big number. And small and big here, I'm just meaning as smaller than 1 or bigger than 1. So we will be using scientific notation somewhat frequently in this class. A little bit of a review of exponents. A positive exponent means 1 multiplied by 10 n times. That's this 10 to the whatever power thing. A negative exponent means 1 divided by 10, however many times we have that exponent. So for example, 10 to the 1 means 10. 10 to the 2 means 10 times 10. There's two 10s. 10 to the 3, we've got 3 10s. 10 to the 4, we've got 4 10s, and so on and so forth. And with our number system, that means that we're talking about moving decimal places. So we're adding a 0 for every exponent that we add on. So 10 is obviously just 10. 10 to the 2 would be 100, so we've got 2 zeros. 10 to the 3, we've got 3 zeros. 10 to the 4, we've got 4 zeros, and so on and so forth. And it's the opposite for our negative exponents. Our negative exponents mean we're dividing by 10 any number of times. So 10 to the minus 1 is 1 over 10. Or if we expressed it as a decimal, 0.1. If we do 10 to the minus 2, 0.01. We've moved it, scooched it, more place. If you've got questions at any point or you're just confused, feel free to let me know. Okay, if we want to put something into scientific notation, we're going to first get our decimal part. So we're going to move the decimal point to get a number between 1 and 10. We want one number to the left of the decimal, a non-zero number. So for our first example, this 94351, the decimal place would be normally after this 1. We're going to scooch it over however many places it takes to get just one number in front of it. So that would be putting it right behind the 9. So that turns into 9.4351. For our other example, we already have a 0 in front of there. We're going to move it backwards so that we've got the 5 in front. You can also skip the counting the places over, but you should count them probably eventually. That's going to be in our next step. So that transforms the decimal part into 5.136. So that's the decimal part. And then for the second part, this is the exponent part. We're going to write that decimal part that we came up with from part 1, multiplied by 10, raised to the number of places we moved the decimal. So there's always going to be a times 10 part. So you can add that in for free every single time. And then we need to count how many places we moved over. If the number is large, or if we're moving to the left, then the exponent is positive. If the number is small, less than 1, the exponent is negative. So if the decimal moved right, because some people like remembering right and left instead, it's going to be a negative exponent. Okay, so 94,351, small number, big number. Big number. You'd love to get paid this amount of money, right? So we're moving the decimal place over. We're moving it 1, 2, 3, 4 spots. So our exponent, it's a big number. It's going to be a positive 4. 9.4351 times 10 to the 4. Our other example, big number, small number. Small number. If we got paid this amount of money, we would not notice. It might honestly be annoying. I'd say no thank you. Okay, so we're going to move the decimal to the right. We moved it 1, 2, 3, 4 spots. And it's a small number, and so we put the negative in front, 10 to the negative 4. And these both capture, these scientific notation forms capture all of the original information that we started with. We'll often be working with even bigger numbers or even smaller numbers, and so we're saving ourselves even more time because there's a lot of extra zeros that would be at the end, or there's a lot of zeros that would be up at the front. But for numbers that are more reasonable like this, it maybe doesn't feel the most useful. Let's do an exercise with this large number. The total U.S. national debt in 2024 was approximately, big number. Express this number in scientific notation. This is for you to try. So go ahead and give it a shot. Come up with the decimal part, count out how many places you move the decimal, and make that your exponent. Oh, right. So we are taking the old national debt. I don't know if it's bigger or smaller. It's probably bigger now. 35 trillion, $2 billion. And we're going to turn that into scientific notation. The place that we're putting our decimal, for the first part, we're going to put it after our first number. So some of us might have skipped and just written in the first number. So our decimal part would be 3.5002. And since all the rest of these are zeros for now, we're just going to get rid of them, save ourselves some time not writing all those zeros. But we also need to figure out how many places did we move over our decimal. And there's two ways that we can do it. One's maybe a little bit faster. The commas in our numbers mean that we've moved over 3 places. So we can count the number of 3, 6, 9, 12. We moved over 12 with the commas, plus 1 to make it lucky 13. So that would be one way that you can do it, or you can just count them each individually. You should come up with the same 13. So we moved 13 places, so we're going to put times 10, because we always have times 10 in our scientific notation. And positive or negative 13? Positive 13. Is there anything that we also should include? Yes, there is. Units. Dollars. Questions? Cool. Another one. Express the number, see there, in scientific notation. Okay, expressing this number in scientific notation, same procedure. We want to move over our decimal place. We're going to move it over till it's behind our first non-zero number, which is 3. So our decimal part is 3.1054. And then we're going to add in our times 10, because we always have the times 10. And we're going to count how many places did we move over. We moved over 1, 2, 3, 4 spots. So there's going to be a 4 up here. Is it going to be positive or negative? It's going to be negative because it's a small number. So that would be our scientific notation. Okay, that's all we're going to talk about scientific notation. We will keep using it. If you've got questions along the way, feel free to ask, or go to Logan's SI sessions. He'd be happy to go over scientific notation with you. Now we're going to get into the basic units of measurement, because most of us grew up with one unit of measurement, and we are mostly going to be using a different system of measurement. So, as an example sentence, when my son was 7, he walked 3, and when he was 4, he could throw his baseball 8 and tell us that his school was 5 away. For many of you, your brain may be filled in some, oh, they probably meant this unit for that thing. When my son was 7 years old, he walked 3 miles, and when he was 4 years old, he could throw his baseball 8 feet and tell us that his school was 5 minutes, 5 miles away, which would be reasonable. We don't have any units there, so it could be when my son was 7 days old, he walked 3 light years, and when he was 4 decades, he could throw his baseball 8 meters and tell us that his school was 5 hours away. It could be that, because we don't have units. It's probably not. But this is an example of units being very important. Units make a big difference. So you never want to write a number by itself. It always needs to have its associated units. Anytime that we have units, I want you to write your units. Or what I've written in other classes, every number needs its unit. Not every number will have units, but most numbers are going to have units. Every number needs its unit. Possibly. This includes when we're doing big, long calculations with multiple steps. Probably every single number that we write is going to have units. They should all maintain their units as we're writing every single one of them, because it'll help you catch mistakes. That's a big part of the reason it helps you catch mistakes. You can see where you went wrong if you do make a mistake, like on an exam. If you get a question wrong, you can go back, look at your work. You can take it to Logan, you can take it to me. We can look at it. If you wrote your work in, we can look at it, and maybe we can figure out why you went wrong. You might be able to catch some of those mistakes by yourself if the numbers get their units with them. I do it the whole semester. Trust me, I don't need to. So I will continue to do it throughout the course. It is annoying at first. Once you get used to it, though, it's not a big deal. It's sort of like putting away things like right after you're done using them, throwing your clothes in the hamper, putting your toothbrush, your toothpaste, whatever, back where it goes, putting your plates and dishes away. It's annoying until you get used to it, and then it's no big deal. You don't even think about it. It's second nature. It's the same thing with writing our units. So put in a little bit of time, a little bit of effort now, and you won't even notice it once we start to get rocking and rolling with the course. Our 2 most common unit systems are the English, the imperial, the customary system. I think those are all technically slightly different, but we're just going to assume that they're all the same. So the English system, that's what we use in the US for the most part. And then what everyone else in the world uses, basically, is the metric system. And so we are going to get an introduction to the metric system units. And I'll try not to ramble on too much about our units of measurement. They are pretty interesting. Okay, so our basic units of measurement, scientists are going to use the International System of Units, or SI units. It's SI in that order because it comes from the French that I'm not going to attempt today. Some of our SI basic units of measurement are given here. So some of our quantities, like if you're measuring length, we're going to be using meters, and that's going to have the symbol M. It would be a good idea. I'm going to cross out candelas and electric current. But you should learn unit symbols, because maybe not all of you are familiar with unit symbols. So things like meters is M, gram is G, Kelvin is K, seconds is S, moles, which we'll get to in a few chapters, is MOL. We're going to primarily be using the shorthand. If you get confused at any point, feel free to just raise a hand and ask. And a lot of the tables that we see are going to be out of our online book, so you can find them there. And oftentimes they're even linked in the slides if you're using them on a tablet or if you're looking at them on a laptop. Okay, our base units. First up, the meter. The meter is our base unit of length. So that's our standard. It's slightly longer than a yard, and it was defined back in 1983 as the distance that light travels in a vacuum in this small fraction of a second, because the speed of light is basically that same number of meters per second. And it's always that number of meters per second in a vacuum. So one of the important things, one of the things that scientists really care about is making sure that their units are replicable. So if I say a meter, if I tell you, hey, I need something cut to 1.5 meters, and you go and you measure something out as 1.5 meters, it's what I'm asking for. And it's exactly what I'm asking for, or it's at least close enough. In the science world, oftentimes, again, we're stretching the boundaries of the really small and the really big, and so tiny little differences in measurement can make a big difference. It used to be that people would measure stuff with like cubits and hands and spans and other sort of weird things, like they show up in the Bible. But those are like based off of the size of a human's body part, or maybe they had like a stick that they would measure stuff out with. And if you're measuring with your stick and I have a different stick, our sticks are maybe not exactly the same length, and so we could run into some issues there. So with our base units, those are typically going to be defined based on constants, like the speed of light. So that's the meter. The base unit for mass is the kilogram. You might expect it to be the gram, but it's actually the kilogram. The kilogram is slightly larger than 2 pounds. Common shortcut is that it's about 2.2 pounds. You can get more decimal places after that if you want to. And the international prototype of the kilogram defined our unit of mass until 2019. So this picture, I'm going to go off on a rant here a little bit. This picture here is showing our international prototype of the kilogram. There are several of them made. I think that this is the original one, or a picture of the original one. And so it's this little cylinder, rounded cylinder of metal on the inside. That is the international prototype of the kilogram. It's about 39 millimeters in diameter and height, so 1.5 inches, not very big. It's 90% platinum and 10% iridium, so you probably won't get one for your house. And despite all of the protections that they put it into, was subject to minuscule changes in mass. So part of the reason they made it out of platinum and iridium is because metals actually lose some of their mass over time, and they can also collect mass over time in the form of dust. But this particular blend loses as little mass as possible. So this piece of metal is held under a little glass dome. You might see these like sometimes for covering cakes, just so that you can like look at the cake and stuff isn't going to fall on it. So that's protecting it maybe from dust or losing some particles. And then it's got another one on top of it, because 2 is better than 1, of course. And then on top of that is this big glass bell that's probably a perfectly flat piece of glass so that it seals perfectly without needing to use grease. And then they also have a place at the top here where you can attach a vacuum hose and pull a vacuum on it so that it reduces the pressure, and there's less dust in there that could get through somehow the first and the second bells to touch our beloved prototype of the kilogram. Everything, all the masses were allegedly based on that little hunk of metal until 2019, and now it's based on the Planck constant, which is a constant, you could look it up, and a Kibble balance, that's this absolute unit of a machine that we're looking at there. A Kibble balance can accurately measure the Planck constant. So the NIST-4 Kibble balance that we're looking at here measured the Planck constant to within 34 parts per billion. So that's this in percentage. So it's a super cool, super accurate measurement of the kilogram. And since the Planck constant doesn't change, people all over the world can just build a kibble balance, like one does, and then measure the Planck constant and then figure out what the kilogram is. A lot of the history stuff with units you don't need to know. It's just, I think it's interesting, so I'm telling you about it. So the kilogram. The kilogram is a measure of mass, which is different from weight. If you wake up in the morning, you step on a scale, you're probably measuring your weight, probably in pounds, that 2.205 pounds per kilogram. Mass is not weight. Mass is a measure of the matter, the amount of matter, the quantity of matter in an object. Weight measures gravitational pull on that matter. So weight depends on gravity. Weight changes with gravity. If you're staying on Earth, your gravity, wherever you are, is going to change a little bit, but it's not going to change enough that it's going to make a difference for most of us. You can't lose weight by just like flying to a different part of the world and stepping on a scale there. You would have to like walk around or like not eat for the whole time that you're on the flight, or other stuff. Weight will change dramatically if I fly to the moon. So if you fly me to the moon, and then you set me on the moon, magically I step on a scale, and magically I've lost 120 pounds. Miracle diet. Unfortunately, if we're measuring the kilograms, the amount of matter that's in my body, it should be the same exact number. I haven't actually lost any mass, which is what I really would care about. So same mass on Earth versus the moon or anywhere else, but the weight would change. So it's a slight, somewhat pedantic difference. We're generally going to assume that we can just convert between the two of them because we'll be operating on Earth. The gram is another common unit of mass. We'll be using that a ton in lab because we're generally going to be weighing small things. So a nickel has a mass of about 5 grams, just to give you an idea of the size of a nickel. And we've got some more conversion factor stuff here. We'll learn about metric prefixes later in the chapter. Questions so far? Cool. Oh. Nope. Okay. Our base unit for time, fortunately for us, it's the same. It's seconds. And the second is defined using an atomic clock. So this is a picture of some dudes standing around an atomic clock. And it measures this many periods of radiation emitted from a particular transition of a cesium-133 atom. So a lot of the time, our clocks, like on our phones, or like when I was younger, we got a VCR that like synced over radio waves to a nuclear clock, and so it would just automatically update the time and it would make sure that it stays on time. One of the nice things about having a reference point like an atomic clock is that all over the world we can sync our clocks together. So like you may notice after maybe a couple months, the oven, the microwave, the car, things that aren't smart devices, oftentimes the time will get off a little bit, and we're not talking about just like daylight savings, right? The time gets off a little bit because the internal mechanism for counting time is slightly different. And so over long periods of time, they start to deviate and they don't show the same time. With an atomic clock, we can always reference back to this is the true time. And usually our phones have the true time because they're updated, connected to the internet, or our laptops, or whatever devices we have. So that's the cool thing about having atomic clocks. And now prefix multipliers. So another cool thing about the metric system versus the English system is that the prefixes, the units, changing between units, is way easier. So it's like something that you can learn relatively quick versus the English system. So let's, little pop quiz with our English system. How many inches are in a foot? 12. Weird number. How many feet are in a yard? 3. That's a different number. How many feet are in a mile? 5,280. That's a third different number. Does anyone know how many feet are in a furlong?
12.
It's a lot. A furlong is the distance around a racehorse track. How many ounces, which ounces, are in a cup? 8. How many cups How many cups are in a pint?
2.
How many quarts are in a gallon?
4.
Cool. So we got some people that are on it. Love that. The metric system, everything just changes by 1 decimal place or multiples of decimal places. So it's always just 10, but like to a different power. So you don't have to memorize 3, 4, 12, 16, 5,280, all these other weird numbers. It's all basically just the same. It'll take a little bit of time for us to learn our metric prefixes, but once we have them down, it's much more pain-free because we can use the same prefixes for grams or kilograms as we use for meters, as we use for even seconds or other units of measurement. We can use them for all of our units. It's not different numbers for all of the different things. So sometimes we'll have to choose a prefix multiplier, and we'll sort of get the hang of that, I think, as we go through the class. We've got an example in here that I don't love, but we'll do it anyway. So generally, we want to pick a unit that's similar in size or smaller than the quantity that you're measuring. So if we're measuring something really, really big, then we want to measure it in really, really big units. I wouldn't want to measure like the distance that it takes me to drive from my house to here, Visalia to Tulare. I wouldn't want to measure that distance in centimeters because that'd be really painful to go out with the meter stick and repeat that over and over. In kilometers, that would be much more easy. I just pull out my kilometer stick and I set that down, and then I walk to the other end and I flip it over, and then I, multiple times, and then we've got probably like a single digit or double digit number of kilometers, and that's a lot more reasonable. Okay, when we're using prefix multipliers, the prefix, like kilo, the prefixes mean, they stand for a number. So they're sort of like variables. We can swap in the number for the prefix. So kilo prefix equals 10 to the 3. And 10 to the 3 is 10 times 10 times 10, because there's 3 10s. That's what the 3 is telling us, which is 1,000. So kilo, if we cut out the middleman, cash for gold. If we cut out the middleman, kilo equals 1,000. So anywhere that we see kilo, we can plug in instead 1,000. So 1 kilometer equals, get rid of the K, turn it into 1,000. 1 kilometer equals 1,000 meters. It's one of the ways that we can do stuff with prefix multipliers. Questions? Cool. Here are some of our prefix multipliers. We will not be using many of them. This is also, this is actually modified from something on Wikipedia, but any of the times that something's linked, it usually goes to the image. There's also a table in the book, but I think it just didn't, it wasn't the format that I liked for putting it in here or something. I had issues with it. So what we would call something in words, we have over here on the far left, so things like trillion, billion, million, and then 1 being a reference. So let's put an arrow there. And then we've got all of our prefixes with their short form, the decimal versions, the power of tens, and the exponent, which is just the exponent from the power of 10. Some of these we're not going to use. So hecto doesn't really get used. So I would say don't bother learning hecto. We're probably not going to get up to peta. I don't think we'll even use tera, but you probably are already a little bit familiar with tera if you have any modern electronic devices that have storage. Phones with terabytes, hard drives with terabytes, solid state drives, Xboxes with terabytes of storage. This is the same tera prefix, and then a smaller unit, gigabytes, smaller than that, megabytes. So megabytes is more like songs, MP3s. Feeling old. MP3s and other things, and maybe large PDF files, photos are going to be in megabytes, and then kilobytes are even smaller than that. Usually Word documents and PDFs, sometimes if they're short, are in the kilobyte size. So these are the same prefixes. So if you're already familiar with data storage prefixes, perfect. That gives you a little bit of a jump start. We're also probably not going to work very much with deci, but we will definitely be using centi. We probably won't get down to pico or femto. I'd like to point out with some of these. So if we look at our reference of 1 and we go past our deca prefix and our centi prefix, right? Deca is 10, like decade, centi, like in centimeters, or centipede, 100. If we get down to milli or up to kilo, when we start moving past, we're moving in increments of 3. It's always going to be intervals of 3 once we get outside of those little weird ones, deca, deci, hecto, centi. So if you remember the order of kilo, mega, giga, tera, kilo is 10 to the 3, and you just add 3 for each step that you move up. And it's the same on the small side. This would be subtracting 3. So we're moving in intervals of 3, or if we were writing them out like in just the base unit, we'd be adding a chunk of 3 zeros and a comma, whatever that is. I'd also like to point out we've got mega up here, which is an M, and we've got milli down here, which is also an M, but it's lowercase m. So big M, lowercase m are drastically different. Mega is 10 to the 6. Milli is 10 to the 3. Unfortunately, lots of people will just haphazardly throw big M onto containers. Like you buy a beverage, and it's got the big M, big L. It's like, this is not megaliters of Celsius, unfortunately. They usually mean milli. We might use mega a little bit, so just be aware that they are the same letter, just one's upper and the other is lower case. Questions about our prefix multipliers? I'm usually nice on the first exam. I'll give you prefix multipliers. So I'll give you something that looks vaguely like this table. You just need to know how to use the table that I'll give you. But you don't have to have them memorized right away, and then hopefully we'll pick up how to learn how to use them later. We'll do this one as an example. This is the one that I don't particularly love. Halfway. So what is a convenient unit to express the dimensions of a mitochondria, the powerhouse of the cell, which is 7.5 times 10 to the minus 7 meters in diameter. So we want to pick one of these 4 units that's convenient for thinking about the size, the 7.5 times 10 to the negative 7 meters in diameter. So we want a unit that's similar to this 10 to the minus 7. So let's go look at our prefix table and find something that's like 10 to the minus 7. So on our prefix table, 10 to the minus 6 is going to be micro. 10 to the minus 9 is going to be nano. So those are both right around the same size of 10 to the minus 7. So micro could work. That's got the Greek letter mu for its prefix. This is going to be a little bigger than the mitochondria. So we'll end up with a number that's less than 1. If we use nano, nano is a smaller unit, it's 10 to the minus 9. This is going to be smaller than the mitochondria. So either of these are in the ballpark, so they would both be good. It's just a matter of if you want to express it as a number that's bigger than 1, or if you're fine expressing it as a decimal. So this in nanometers, if I'm doing it correctly in my head, 750 nanometers, that's nice. Or it'd be 0.75 micrometers, or microns, as they're often called. So it would be one of these, C or D. I would probably pick D because I like number bigger than 1 a little better. We can also use our units to make other units. Gives me a meme idea. A derived unit, we'll encounter derived units, is formed from other units. Derived meaning it comes from something, so it's coming from other units. We put units together to make new units. We love new units. Many units of volume and area. We don't really talk about area very much in this class, but area would also fit in there. Many of those are derived units. Any unit of length, something that we'd measure in meters, feet, inches, centimeters, etc. If you cube it, if you raise it to the power of 3, becomes a unit of volume. So things like cubic meters, the cubic means that it's meters, or that it's raised to the 3rd power. Cubic centimeters, we've got centimeters raised to the 3rd power. So cm to the 3. Cubic millimeters, those would all be examples of units of volume because they're based on another unit. In the picture, this is a 1 meter by 1 meter by 1 meter cube that my mother is sitting in at like a science museum. It's not just like a thing that she does. She was visiting a science museum and wanted to take a picture for her slides, and I borrowed it. Other units, like liters and milliliters, like a 2 liter of Coke, or other beverages, and milliliters are volume units, but they're not derived units. And then just for your reference, 1 liter is similar in size to a quart. Questions about derived units or prefixes? Cool. Now on to our nemesis, perhaps. Significant figures. He was not talking to me. Significant figures. So we, in science, care about significant figures, which is a concept that we're going to learn about here. Significant figures is just making sure that we are reflecting the precision of our measurement. It's like if I measure something with a ruler versus if I measure something with like a very fancy like laser microscope, not microscope, like a laser distance measuring system, I'm probably going to get a better result, hopefully from the laser system versus just a standard 1-foot ruler. We want to be able to reflect how precise our measurements are in our calculations. One example, nickels come in whole numbers. You can count 5 nickels and it means 5 nickels. These are my nickels. I have those. I think I have them at home, but I found nickels at my house. So these nickels, these 5 nickels, would anyone dispute my claim that that is a picture of 5 nickels? Could it be 4.9 nickels? Could it be 5.01 nickels? No, because it's whole countable units. Similarly, counting students in the class, if I counted up the number of like people in the classroom, I would come up with a whole number. Let's say that it's 58. I count up 58 people. If I count up 58 people, great, we've got a relatively full class. If I counted up 57.5 people, what does that mean? Somebody's going to jail, right? Because you should not have half a student. We're all slightly different sizes, but we all count as one student, one person, right? So those are examples, things that you can like count on your fingers, and there's no dispute. These will be kind of a weird magical outlier in our significant figures discussion. On the other hand, if you have this bar of gold also at my house, if you've got this giant 250 kilogram bar of fine gold, if I tell you that it's 50% gold, that's not as impressive. It's still impressive because that's still a lot of gold, but it's not as impressive as saying it's 99.99% gold, right? Those two values are quite different. It would also be inaccurate to say probably that it's pure gold because there's probably a little bit of something in there that's not gold. And so in these instances, we really care about how precisely we measure the quality of the gold that was in there, because it can make a big difference. Another example, this might be a little bit of old data, but scientists have concluded that the average global temperature risen by 0.7 degrees Celsius, or like more than 1 degree Fahrenheit, since 1880. And that's based on analysis of records from thousands of temperature measuring stations around the world. So all over the world, lots of different temperature measuring stations. They figured out it's gone up 0.7 degrees Celsius. If you add more zeros, or if you add more decimal places to that, it's different information. So if you say that it's gone up by 0.70 degrees Celsius, or 0.700 degrees Celsius, most of us have probably seen measurements that go out to 2 or 3 decimal places in degrees Celsius, much less degrees Fahrenheit. The temperature systems that we have at home, on our phone, if you look at the weather, it doesn't even tell you a decimal usually. So if we added extra things, or if we just use the average displayed by the computer, which might be this number, that's like a crazy amount of decimal places. That would mean that we measured at all of those temperature stations all the way down to however many decimal places this is, all over the world at thousands of different points for decades. We probably didn't do that. That would be an egregious overstep in the number of decimal places, but we can pretty confidently say 0.7. And we use a standard way of reporting measured quantities, which is our scientific notation, significant figures. And anytime that we're doing significant figures, our uncertainty is indicated by the last reported digit. So the last number in any number, the last digit in any number, has a little plus or minus baked into it. So for example, this 0.7, that could be 0.65, and it was like close enough that it got rounded up. It could be bigger, it could be 0.74, and it got rounded down. There's a little bit of wiggle room because of the unit that we used. Like if I measured the length of the room in my height, like I just lay down on the ground and then roll over a few times, and then I just reported it in the number of, Mr. K's that the room is wide, it would probably round to a number, but it would have really been between two numbers. Does that make sense? Okay. I come up with weird analogies sometimes. They don't always work. Okay, so we write our numbers. So every digit is certain. We're 100% sure about these 4 numbers. And this 2 has a little plus or minus in it. So first 4 digits, we're absolutely sure that those ones we locked in. That 5th one could be a little plus, could be a little minus. The greater the precision of the measurement, usually that also goes with cost. It's more expensive. The greater the number of digits reported. We have scales in our lab that can measure more decimal places than this for grams, but they're pretty expensive. Okay, some examples, because we love examples. If we take our 5-cent piece and we put it on a ruler that's in centimeters, because we're in a science class, we put it on this ruler and we measure it. We've lined up the edge so that it's starting at the 0, and then the other end is where we're measuring. So I've got some lines that I added in so that we can see where the end part is. So we are definitely past 2 centimeters, right? We're between 2 and 3 centimeters. So we're for sure past 2 centimeters. And then we've got subdivision markings. Another really nice thing about the metric system is that all of the subdivisions, like when you're measuring stuff, it's just like always the same. It's 1 more decimal place over, versus on like a ruler that's inches and feet, you've got like 1/2 inch, quarter of an inch, eighth of an inch, 16th of an inch, 32nd of an inch, maybe even 64th of an inch. Those get really annoying sometimes to figure out, like when you're kind of in the middle. It can be really annoying to figure out what your reading is. We don't have that problem in the metric system. So we're past the 2. We're past the first little mark. This would be 2.1. Would anyone dispute that we're past the 2.1? Does anyone think we're not past the 2.1? Cool. So everyone agrees we're past the 2.1. Are we to the next mark, the 2.2? No. So we can lock in. We would lock in that 2.1, and then it's up to us in our best estimate to figure out how far is it. Computer, enhance. So we're looking at this line up here. How far is it between 2.1 and 2.2? Usually I tell people on a scale of 0 to 9, 0 being it's not there, it's right on the first mark. 9 being it's right up against the next mark. 0 to 9, how far is it? What do we think? Could be 4. It's probably not 5, right? It doesn't quite look like it's halfway there. It's a little bit before halfway. So maybe 4, maybe 3. 2 that I have in the slide, maybe a bad estimate. Question?
It looks like it's 3/5 of the way there. Because if you look at the pixels, it's usually pixels in between.
It might be 3/5 of the way there. It might be 3/5 of the way not there. Because it looks like it's more to the left than to the right. Because 3/5 would be 0.6. And it looks like it's 0.4. So, but there's a 3/5 in there somewhere. Okay, so we can definitely lock in the 2.1, but then there's maybe some dispute about what the next number is. I wrote the 2, which is probably wrong, but it could be 3, and it could be 4, and then we would want to make sure that we include our centimeters. So if you wrote 2.13, and your lab partner wrote 2.14, then you can get in a fist fight about it in a video game. Or you can play rock, paper, scissors and figure out whose number you're going to go with, or you could just have different numbers. That's also fine. Usually when we're doing this estimate part, there is going to be some disagreement. If we polled the entire class secretly, anonymously, people would come up with different numbers for this. But as long as we can all sort of agree, yeah, it's reasonable, then it's a good estimate. All right, this slide. So this balance has markings every 1 kilogram. So we're going to estimate to the 10th place. Whenever we're doing an estimate, we're estimating 1 more place. One extra place value. So our balance is in 1 kilogram. So we're going to estimate over the next one. That would be the tenths. And I say this slide because I had trouble finding pictures of people standing on scales that just didn't have the dogs out. This person, fortunately, was wearing socks. Thank you. So if we zoom in on the scale, our 115 mark is here. We're 2 more past that, but not to the 120. So we're 2 more past 115, 116, 117. We're past the 117. How far between 117 and 118? Could be 0.2 this time. If you said 0.5, I think you're crazy. 0.2, 0.1, maybe 0.3, somewhere in there, those would all be perfectly fine readings. So this last digit, that's the estimate part. Okay, and then we've got this 4-beam balance with the indestructible Nokia phone. So this scale is a little complicated. We generally will not be using these scales. I think they're cool. 4 arms is crazy. I've got one in my office that's got 3 arms. The way that these scales work is we've got a bar for each place value. So our very back bar is the biggest bar, a big weight on there, and every time that we move that over and lock it into a spot, it's going to be initially 0. The place that it's locked in here is 100 grams, and there's also an option way in the back on the right side for 200 grams. So we would set that first, and then we'd count over how many spots we need to move our 10 grams until it's kind of, we're between points, but it's not quite tipped over. And then we would do the ones place, and then this last one doesn't lock in. It's a smooth sliding scale so that we can do that estimating part. And these are called balances. The ones that we use in the lab that are digital are also called balances, but they're called balances because we're balancing the weight on those arms versus the weight of the object, and we're trying to get them to be nice and even, which is indicated by this arrow pointing at the 0 mark. That means that we are right about on the point. We generally will not be using these because partly they're slow. Okay, so we do a close-up. We've got 100, 30, 0 in our one place. So that's where we're locking in the 130. 100, 3, 0. And then on our smallest little beam up here, we've got our 0.5. We're definitely past the 0.5. And it gets a little grainy. Just imagine that there's a little point there. There is really there's actually a point there. It gets a little grainy. So that little point, right, looked to me like it was right on the mark. That first subdivision. So it's on the first tick, and then the 0. That's the estimate. So I'm still doing an estimate, even though it looks like it's right on the mark. That estimate is, it's right on the mark. It's not a little bit over, it's not a little bit under, it's right on it. So we just add a 0. The 0 lets other scientists know later we made sure that we did the estimate. If you don't include that 0, then it looks like the 1 is estimated. Hopefully that's making sense. For estimating things, this 0, if it's a 0, if it's right on the mark, that's usually where people forget to include it as an estimate. You do still have to include that 0. It's very important. Okay, one for you to try with measuring temperature. So you're staying in a cabin in the mountains during the winter. How nice. And you want to figure out how much to bundle up before going outside. You have an outdoor thermometer, and you obtain the reading shown. Please record the temperature reading to the correct number of digits. All right, we're doing a temperature reading, an analog reading. We have to come up with the numbers. We're looking at the little needle here. The needle is over in the negative zone, so negative 10 is here. It's going to be negative something. We are not to the negative 10. We're between 0 and negative 10. If we count backwards to negative 10, we're going to have negative 9. That's not a great color. Negative 8. Negative 7. So we are between negative 7 and negative 8. If we're between negative 7 and negative 8, what would that mean that we're locking in? Negative 7. So sometimes our glassware is going to be, like the numbering is going to go backwards of how we would expect, or in this case, we've got the negative numbers, and so we have to either remind ourselves, we have to be on top of it, know that we're increasing one direction versus the other. Anyway, so we're between 7 and 8, so we're locking in the minus 7, and then from the minus 7 on the right to the minus 8 on the left, how far over are we? Got some guesses for 0.8? 0.8 might work. 0.8's like on the high side. It looks to me, now that we're zoomed in, it looks to me like we are definitely past halfway, so we definitely lock in more than 5, but maybe 6, 7, 8. 7.6. We could increase that by 1. We could maybe even increase that by 2. So any of those would be reasonable readings. Except, what did we forget? Units, degrees Celsius. So we'd want to add in our degrees Celsius for those as well. questions about that? We will be doing a lab where we get to practice with taking measurements. So if you're confused, we'll get there. Okay, now on to significant figures. We've got a quiz on significant figures in 2 weeks to hopefully help us learn significant figures. I think that's before our first exam. Yes, it's a week before our first exam. So that'll hopefully give us some feedback about how we're doing on the significant figures part, because that does also feature on exam 1, and we're going to use significant figures throughout the course. So first, we need to count significant figures. Significant figures are non-placeholding digits in a measurement. What that means is a couple of things. We can go through it with a set of rules. So first, all non-zero digits are significant. Anything that's not a zero is significant, always. Nice. So that's like most of the numbers that we're going to encounter. Most of the digits that we'll encounter, those are significant. So the 1, the 5, the other ones, those are significant figures. Interior zeros between non-zero numbers, those are also significant. So we've got some interior zeros shown there. Those are also always going to be significant. Trailing zeros with a written decimal point are significant. And sometimes we'll also do silly things like writing 40 and then the period or the decimal place, and that would also make that zero significant. So anything that's not a zero, always significant. It's just the zeros where it can be a little bit less clear. So non-zero digits are significant. Interior zeros between non-zero numbers are significant. Trailing zeros with the written decimal point are also significant. But wait, there's more. Zeros before an implied decimal point are ambiguous depending on who you ask. Some instructors say that they're always significant. Some say that they're never significant. In my class, they're ambiguous. And we should avoid them with scientific notation. If you just see one of these numbers out in the wild, 50,000, we didn't take the measurement. We don't know how many significant figures were intended. But it's at least 1, because we've got the 5. That's a non-zero number. And then any number of zeros, including up to all of them, could be significant too. So for example, this would be at least 1. It could be up to 5 significant figures. If we know how many significant figures it's supposed to have, we can instead write it in scientific notation. In scientific notation, we'll have a written decimal point. So like, let's say that it's 3 significant figures. We would write it as 5.00, so that's our 3 significant figures. They're after a decimal point, and so they are significant. And then we times 10 to the 4, because it's a big number, so it's a positive exponent, and we had moved the decimal over 4 spots. And when a number is written in scientific notation, all of the trailing zeros are significant. This is, again, because of that written decimal point. And we've got one more rule. Our one last rule is that leading zeros are not significant. So like in numbers that are smaller than 1, oftentimes those leading zeros will not be significant. Always they'll not be significant. However, a word of caution, warning, a more relevant word of caution, those leading zeros, although they're not significant figures, are still important that we put them there. So if you write in 0.0005, that's a very small number. If you were like, oh, those zeros aren't important, we'll get rid of them, and you just write 5, that's a very different number. Right? So it's important that we write them. They just don't count for significant figures. Questions about our 5 rules for significant figures? If you're already confused, don't worry. It is a little confusing. Logan would be more than happy to talk about it with you during his SI session today from 1 to 3 over in the library STEM room. Or you could also ask us during lab because we will have some free time in there. Okay, back to the nickels that we talked about earlier, or the students that we talked about earlier. Those are examples of exact numbers. Exact numbers we consider having an unlimited number of significant figures. So do not consider them in calculations. You can just ignore these exact numbers in calculations. So examples of exact numbers, exact counting of discrete objects. These are not objects that you keep on the down low. This is a different kind of discrete. You can also interpret this as countable. So if you can count it up and you're 100% sure that it's that number, like students, desks, chairs, flags, stars on the flag, nickels, other things like that, pencils, those would all be exact counting of discrete objects. So those would be countable. Those are going to have an unlimited number of significant figures because there's no uncertainty about the number that we have. We also have integral numbers that are part of an equation, like diameter equals 2 radius. That 2 is an integral part of that equation, and so that's also not going to limit our number of significant figures. Defined quantities, like metric prefixes, are also not going to affect our number of significant figures. There will also be things like 12 inches equals 1 foot. One of those is defined based on the other one, so it's exactly 12 inches. Generally, if you're working within the same system, if you're working with English, American units, or if you're working with metric units, usually if you're staying within that system of units, it's going to be exact. Generally, conversion factors where you're moving between the two are not exact, with one important exception. 2.54 centimeters equals 1 inch is exact. On a handout that I have to send to get printed for you, some of these do have about if it's exact or not. I think this is one of them. And on exams, I think this also gets this. It tells you that it's exact behind it. So this is one weird exception because it was really close to being exact. It was like 2.540007 or something like that. And people around the world were like, hey, can we just, like, it's really close. Can we just round it? And everyone was like, yeah, that seems reasonable. Let's just round it. And by people, I mean, like, leading scientists from nations across the world or something like that. So now it's exact. Generally not exact. Usually if there is a decimal part, it's not exact. Just generally. Okay, and then the last slide that we'll go over today is just figuring out the number of figures that are significant. So how many significant figures do we have in each of these numbers? We've got 5.87. How many significant figures? It's 3, because we've got only non-zero numbers. They're all non-zero numbers. B, we've got 0.031. How many significant figures do we have for this one? It's 2, because we've got 2 non-zero numbers, and the leading zero's not significant. We still need those leading zeros there, but they are not counted as significant figures. Okay, next one, 52.90. This one's going to be 4. We've got 3 significant figures from non-zero numbers, and we've also got a trailing zero with a written decimal place. So 3 non-zero plus 1 0 after with decimal place. Write that as confusingly as possible. All right, 00.2001. We've got our 2 and our 1. Those are definitely significant. We've got these zeros up in the front. We've seen leading zeros before, not significant. And then we've got interior zeros. Those interior zeros are significant because they're between 2 non-zero numbers. Right? They're between the 2 and the 1. So this will be 4 sig figs. And about 500. It's at least 1. Are the trailing zeros significant? Maybe. It could be. It could be that they're both significant. It could be that neither of them is significant. So this is ambiguous, meaning that we're not sure. It's not clear. It's at least 1. If we wanted to play it safe, if this was like in a calculation, if we wanted to play it safe in terms of like not overestimating our precision, the safest way to do that would be assume that it's 1 significant figure. But it could be up to 3 significant figures. Could be 2 or 3, depending on if those zeros are significant. If we wrote this number, if we came up with this number, we measured the number, we would want to make sure we write it in a way that shows that those are either not significant, one of them significant, or both of them are significant. So we'd want to write it in a way that it's not ambiguous like it is written here. And then the last one, 6 atoms. We got a guess for 1. We've got a guess for unlimited. Those are the 2 guesses that I expect. It is unlimited. Exact. So, unlimited significant figures. Believe it or not, we can't actually count up atoms. It's just really expensive. Any questions at all about stuff that we covered today? All right, then we'll pick up here next week, Tuesday. If I didn't call you for roll,